restart the presentation. All right, thank you. Okay, so next we have the autonomous shopping assistant.
I'm Eric Evans, Elijah Grubbs, Chris Welford. Jumping through the slides quick here. Our team is the autonomous shopping assistant. So we'll begin. As an introduction, one of the main focuses of our project was to use a newer technology called ultra-wideband triangulation to basically do what GPS does for outdoor autonomous vehicles for indoor where GPS is not going to be as reliable. Ultra-wideband is changing what's possible with indoor localization. The way it works is we have a network of anchors that you would install in the room. And so in our case, we have 4 anchors installed in the room running on 5-volt batteries. And those 4 anchors would be able to track 2 tags in the environment and give us really accurate positional data. So it's still really new technology. When we first started looking into it, we were only able to find one company from Germany selling custom-made PCB boards that we could interface quickly with their software, install the chips, and move forward with that.
So as far as our research has found, we're the first ones who are actually trying to use the ultra-wideband technology for indoor following. We've only managed to find other applications that are just looking for localization. So our goal is to use the accuracy and the range that this new technology would provide in order to allow us to create an autonomous following system.
So one of the main inspirations behind the project was to create a following system that worked indoors. Most following systems today work using outdoor GPS technology, and they're not very effective indoors. So our design decision was to make ultra-wideband the technique to allow an accurate indoor positioning system without the reliability and need for GPS.
So our project requirements going into it, we wanted to adapt these highly accurate indoor positioning technologies for autonomous following systems. We wanted the cart to provide mobility assistance, so if people are, have trouble pushing heavy cart loads, this would do that for them. It also allows users to focus on primary tasks. If your kids are running around, you can keep an eye on your kids. And then also we wanted to have a reliable obstacle avoidance system implemented so that it's safe in these public environments.
Like Eric just said, our goals were to create an autonomous shopping cart that could follow you in the store, and it would avoid obstacles such as shelves or other people. When you're walking up to a shelf to grab an item, it would then position itself next to the shelf without running into other objects, so that you could easily grab it from the shelf and put the item into the cart. So the details of the ultra-wideband, it's an anchor tag system. The anchors would be mounted around the room, and then they would sense the different tags and use the readings from each of the different anchors, send over UDP, and then be able to triangulate the location from that. Our goal was then to create software that would take that localization data and create a following algorithm. A couple issues we had as we were going about it. We were ordering these from Germany, and they were still very new, so we didn't know at the time that we were ordering development samples. So we ended up having to do, for the first time in our lives, surface mount soldering for fairly small components. Then later on we also realized that we had to keep the anchors in a vertical position. So we ended up designing through CAD systems our own 3D printed mounts for the Locolino anchors. Also in our communications with the manufacturer of the PCBs, they were very helpful as far as they could be, but we ran into language and time zone barriers. It was difficult to communicate between everybody. And later on in the semester, we learned that we needed an additional anchor in order to actually overcome catastrophic failure that was apparently known, but was not made known to us.
So how our shopping cart system works is we have 2 primary wheelchair motors that operate the cart, and those are controlled by a Sabertooth 25 amp motor controller. And the main unit that's powering everything are 2 12-volt batteries, one of which was primarily used to, use the disengage for the motors. However, we ended up taking those out, so we only really need one primary battery source for the entire system. We have several Arduinos that are in communication with the motor controller, and those are effectively communicating over serial to issue commands to the wheelchair motors that are issued from Wi-Fi over, like I said, the serial connection to communicate. So one of the problems that we have with driving currently is that the front wheels are not very well aligned. As you can see on the shopping cart, they're kind of rusty at the edges, and they offer, like the previous groups have experienced misalignment. And there was a lot of complicated wiring involved because we had multiple Arduinos and we had a bunch of sensors that are mounted on the cart itself. So with all these moving parts, things kept getting unhinged and disconnected. And so we had to utilize different techniques to clean up the wires and make it as efficient and tight as possible to allow a functioning system that's in dynamic motion.
So for the obstacle avoidance system, we originally were going to use ultrasonic range sensors, but we decided to go with 6 time-of-flight micro LiDAR sensors. The reason we went with these sensors is they give us much more accurate ranging. The only problem is that they are a very finite, it's like shooting a laser as opposed to a cone. And so these 6 sensors are running through a MUX and then connected to an Arduino Uno over I2C protocol. We decided to use 6 servos to attach these sensors and have the sensors pan. And the reason for that is since it is just a laser, we wanted to make sure that we had a full 360-degree coverage of the cart. In future implementations where it was just cheaper for us to buy some servos and pan them as opposed to buying another MUX and more sensors. So we did that was mostly a cost issue. In a real implementation, we just have a lot more of these sensors around the cart. It's currently set up with a front, left, right, and rear flag system that's designed to disable motion in a particular direction. So if we're driving through an aisle and something gets in front of it, I'm still allowed to turn left or right. If something's on the left and in the front, I can't go forward or left, but I can still go to the right. And then as we'll demo later, if you block the front, the left, and the right, if it went into the corner, the cart executes a contingency plan where it automatically reverses either until one of the flags opens up or until something triggers the rear sensor. And so some of the problems that we ran into with this system is, like Elijah said also, this is a very complicated wiring schematic, which we'll show you in a sec here. But a lot of the wiring mistakes led to malfunctioning MUX channels as well, so we had to kind of move around. I think we have 8 channels, we're using 6. I think we fried one of the channels, just didn't want to work correctly. And because of the complex wiring, it was tedious to debug and tedious to isolate the wiring errors. And then the most common issues after a lot of testing with the motion of the servos, we've ended up having problems with the actual wiring, shaking the solders loose on the pins. And as soon as one of those wires becomes disconnected, the way our software works is when it pings that sensor to pull data, it's calling a function from the libraries for these sensors, and it would essentially just freeze up our obstacle avoidance completely. And at the same time, it was causing issues. Since the whole system has common ground, as soon as some of those connections came out, we were seeing weird drive jitter, and we believe that to be an issue caused by the common ground becoming disconnected. So we're going to show a quick demo of the driving over Wi-Fi. So this is driving with obstacle avoidance. It has sound, but
The volume
Turn down the volume.
Volume.
No,
on
on
the
the
computer.
the computer itself.
The live demo of the autonomous shopping assistant. The live demo of the autonomous shopping assistant. We're currently not running our servos because as the servos are turning, it's shaking one of our many solder connections loose. We don't know which one it is, but that's causing an error in the obstacle avoidance system when a particular sensor gets pinged. So we're going to give power to the system with our kill switch. We'll notice down here, that's the rear sensor picking me up currently, that blue light. It's our rear sensor. If I back away, you'll notice that blue light should go off. And drive forward. And we're gonna stop the cart by Elijah kind of getting in front of it here. And we'll notice that we have a green light at the bottom here, showing that we're still trying to drive forward, but the forward sensor, which is the green light, kind of hard to see with the light on, I don't know your sensors. That green light on means the front flag is currently locked. So now what we're gonna do is we're gonna twist right here. And I'll go ahead and stop it with the right sensor. So you'll notice I hit any of our right sensors will stop the right motion. Let's go ahead and twist to the right again to reorient. So we're twisting up until it gets to me. It's gonna go ahead and stop. Again with the servo. Okay, and so we're gonna pause there and actually do a live demo of the obstacle avoidance system. So if you guys wanna fire it up. And camera off. Okay. So I'm gonna show off some of the lights that we created just to help with testing purposes. So down here at the bottom, you'll see that blue light came on, and that's because it's picking me up at the rear sensor. If I get out of the way, that blue light will go off. And so for instance, let's trigger the right sensor. You'll see that right yellow light came on. Front sensor is the green light. Hopefully it's coming through. And then the left light. And so we're going to show off our contingency plan. So what we're going to do is Chris and Elijah are going to cover the left, right, and front flags. And what that's going to do is immediately, well, I got to get out of the way of the back sensor. When the back sensor is free, it'll back up either until we clear a flag. So Elijah got out of the way and it's opened up. Or if I get in the way, it'll also stop the car as well. So that's pretty much that on the demo side. Okay, and so this is our schematic for the whole system. All the local sensors just run off of a 5-volt USB battery pack. Each one of them has a Wi-Fi chip on board, or sorry, all of the anchors have a Wi-Fi chip on board, and each one of them have an ultra-wideband chip on board. So when the anchors triangulate the tags, they send the location data over Wi-Fi to the computer calculates that. I'm going to spend too much time on this, but this is essentially the wiring schematic, so you can see we got a lot of stuff going on. Okay, this is our following algorithm. So the way we decided to do it was basically you fire the cart on, drive the cart maybe 2 feet, you're collecting this XY pair, that XY pair, then we pull the user position. At that point with those XY pairs, we can calculate the distance between all of them and the angles. Calculate the angle to turn the cart. If the cart would turn, drive towards the user. Next one. We would save the old cart position, the new cart position at where the user was. Here's the new user position. Do the same thing again. Just do all the calculations, make the turn, and drive the cart. So. Yeah, real quick. This demo is with us actually. So we've mapped the room with XY coordinates. I'm reading out the XY coordinate of that particular spot. This is real jittery, but this is showing you how fast the local Linos are updating the XY positions. So we're getting them real quick.
8.5.
And then Chris will show you some of the, I think it's good enough. So this is some of our tests.
All right, so like I said before, at the end of the semester, we had to get a 4th anchor in order to overcome a catastrophic error that was unknown to us. Even with this 4th anchor, the results were not great. We were actually getting location data, but it was not the not scaled to the actual dimensions of the room that we had set it up in. So in order to try and overcome that and create a functioning prototype, we created our own software that would take whatever values we were getting for the XY coordinates and scale them according to the dimensions of the room. So as you can see here, we took the actual X and Y coordinates. That's what that video was Eric standing on the actual XY coordinates, and then I would give the values that the local Lino system was saying that it was at, and then we were testing our algorithm for scaling. And so you can see in general it's fairly close. We're within 1 to 2 feet, which for an initial prototype is actually pretty good and fairly spot on.
So the final results, we have a fully functioning cart system that can be operated over Wi-Fi. It has a built-in obstacle avoidance, and effectively is able to, to move around obstacles and has a full-on contingency plan built in. We have a preliminary setup for the Localino integration. However, because of the technological constraints, we weren't able to implement that due to the hardware. On our cost analysis, we had a budget around $1,200. However, we ended up spending around $1,400, $700 of which was the Localino system that doesn't work. So that kind of put us over budget. We could have done this more efficiently if we would have had a more efficient ultra-wideband.
If we had more time, we would have been able to create our own ultra-wideband system. It would have lowered the cost.
And we're at the point where it basically is working. It's just we didn't get enough time to pull the information over UDP and implement it with the drive commands. So we're right there, didn't quite get there.
So indoor autonomous systems, our actual goal for this isn't just to limit it to shopping carts. This technology for following can be implemented for following luggage that can be just utilized in the airport. You can like pair your phone with the ultra-wideband phone case with the airport system, and then you have your luggage following you around the airport. You can put it into things like strollers, a lot of applications in manufacturing where you're going to have heavy loads that need to be brought around warehouses, but this way it would now be automated so it would follow you, but you wouldn't have to worry about being able to push the carts around.
And then just real quickly for the end here, our future work, our team was lucky enough to get full funding to be part of the CSUF Startup Incubator. So we're currently working with them. And basically our goal is to do something similar with indoor autonomous, but without the need for infrastructure. So these are our design goals: low cost, low energy, infrastructureless, point-to-point position detection, indoor or outdoor operation, light or dark environments, loud and quiet environments, and 30 to 40 foot range. And we're hoping that a system like this can be used for all types of different following applications. Questions?